Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and materials subject. So in this subject already in previous sessions, we have discussed about types of stresses and types of strains and the relation between stress and strain and elastic constants, and we have discussed about shear force and bending moment diagrams. So how to calculate shear force and how to calculate bending moment for various beams when a load acting on the beams, that is according to the types of loads. We have calculated shear force and bending moment values, and then we have drawn shear force and bending moment diagrams for different beams. So today I will explain about some more beams shear force and bending moment diagrams. We have seen cantilever beams, simply supported beam, and with point load, without point load, with UDL, combination of these two already we have seen in previous sessions. But in this, so I want to explain about the shear force and bending moment diagrams for uniformly varying load from 0 at each end to W for unit length at the center. So here, first of all, we will discuss about CO2. So that is course outcome. At the end of the course, the student should be able to answer, illustrate the shear force and bending moment distribution in beams for analyzing the structural behavior under various loads. So after completion of this module, the students are able to understand what is shear force and what is bending moment, and then how to illustrate the shear force and bending moment distribution for various beams. They can answer. They can able to draw, so that the outcome of this module, the shear force and bending moment diagrams, they have to study about different types of beams, and also the student can analyzing the structural behavior under various loads. So we are discussing all those things towards CO2 achievement. So the important points for drawing shear force and bending moment diagrams. So the important points already you have seen in the previous sessions. But before drawing the shear force and bending moment for every beam, you should follow the some rules. So those rules are, those points are given here. One is, consider the left or the right portion of the section. So it means first you have to divide the beam into two parts, two sections. So that is, whenever you section the beam, then separate left portion and right hand side portion. So consider any one, either left or right. So add the forces, including reaction, normal to the beam on one of the portion. If right portion of the section is chosen, the force on the right portion acting downwards is positive, while a force acting upwards is negative. So you are, suppose the right portion of the section is selecting, you selected that the force on the right portion acting downwards is positive. The downwards positive and the right negative is upwards. So right side portion. Suppose in left hand side, the downward is negative and upward is positive. In the left section, is Susan. A force on the left portion acting upwards is positive, while a force acting downwards is negative. Clear? These are the important points, and some more points we will see. The positive values of shear force and bending moments are plotted above the baseline. So for drawing the shear force and bending moment, first of all you should draw the baseline. So above the baseline, positive values, below the baseline, negative values you have to draw. Okay, the shear force diagram will increase or decrease suddenly. That is by a vertical straight line at a section where there is a vertical point load. So the shear force between any two vertical loads will be constant, and hence the shear force diagram between two vertical loads will be horizontal. So the bending moment at the two supports of a simply supported beam and at the free end of a cantilever beam will be 0. The shear force between any two vertical loads will be constant. The shear force diagram between two vertical loads will be horizontal. So the bending moment at the two supports of a simply supported beam and at the free end of a cantilever will be 0. So these are the important points for drawing shear force and bending moment diagrams. In this session today, we will see the simply supported beam carrying a uniformly varying load from 0 at each end, at A and B 0 to W per meter length, unit length at the center. So this is the given condition. So we have learned in previous session simply supported beam carrying a point load. So like this, simply supported beam A and B, the point load at its center C. We have seen and also drawn a shear force and bending moment diagram for this beam. And also for UDL case also we have seen. UDL with point load also we consider, and then very eccentric load, eccentric point load also we have seen. But in this diagram, given condition is simply supported beam carrying a uniformly distributed load, but this load is UDL, but the uniform distributed but varying load. That's why UVL. You can say a UVL, uniformly varying load from 0 at each end and to W. So A and B are, let us assume, reaction forces. So let RA and R be the supports. So the reaction forces are at these points RA and RB. This load diagram, the length in between these supports are L, and at center L by 2, half of the distance, and take section at section X. So that is with a distance X from its end point A, and this point is noted as D. The maximum, the center distance, the height of the load is 0, that is O. So this is a given diagram load. For this load diagram, you have to draw the shear force and bending moment diagrams. So first of all, need to calculate reaction forces, and then what is the shear force at A, What is the shear force at C? Clear. What is the shear force at a particular section? This is a important thing. So now calculate shear force when you total load on this beam. So the total load on the beam is nothing but the area of the triangle. Which triangle? AOB. The total load. So here, see, the figure shows a beam of length L, simply supported at the ends A and B, carrying uniformly varying load from 0 at each end to W for unit length at the center. The reactions at the supports will be equal. The reactions at the supports be equal, and the magnitude will be half of the total load on the entire length. So here the reaction supports are equal. So that is RA and RB. So RA is equal to RB. And the magnitude will be half of the total load. So the magnitude half of the total load. So total load on the entire length. So as the load is symmetrical on the beam, the load is symmetrical. So this, the UDL load like this, and A and B reaction forces and C. So this is symmetrical. So first calculate total load. If you don't know the total load, you can't calculate reaction forces RA and RB. So for this, total load on the beam is equal to area of the AOB triangle. So this is total load on the beam. Okay. So now the area of the AOB calculate. Half multiply with AOB, AB multiply with OC or CO. So what is the AB value? AB is length L and CO is W. So the total load on the beam is WL by 2. So this is the total load on the beam. Now calculate RA and RB. RA and RB is equal to half of the total load. RA reaction force at A, RA is equal to RB is equal to half of the total load. The total load is WL by 2. So WL by 2 by 2. So this is WL by 4. So the reaction force, support reaction force at their the reaction force at the supports RA and RB magnitude is equal WL by 4. So now we have calculated RA and RB. Now calculate the shear force at a section at a point A at section X and then section at point B. So here first assume let X is the section and the distance is X from its point A, the distance is X. Clear? So here at section X, the point noted as D. So a triangle is AXD. So calculate the XD, the AXD area. So now see here, so calculate RA and RB over and shear force. Shear force at section X. Shear force at section X. So how do you calculate the shear force at X? At X is equal to, at section X is equal to RA, reaction force acting upwards, minus the load on the length AX. So the load on the beam length AX. Why? Because up to X length the section is there. See, up to here X. So what is the load on this? So the load is here. So take a triangle, similar triangles. So RA, WL by 4. But load on the beam length AX. So that is load on the beam length AX is equal to, load on the beam length AX is equal to area of triangle AXD. Area of triangle AXD. So here the area of triangle AXD half into AX multiplied with XD. But how do you calculate XD? We don't know XD. So take similar triangles. Similar triangles from the diagram. So what is the diagram here? The similar triangles diagram. So once I can draw this diagram, A and B. So that is at X section, the D point, this is X, and C, O, this is L by 2, and entire length is L. So similar triangles here, XD by AX is equal to CO by AC. So from this is apply similar triangle rule. So that in this now substitute XD, we don't know, need to calculate. AX is equal to X, CO is equal to W by AC is equal to L by 2. So XD is equal to W into X by L by 2. So now take this value in this, substitute. So in this substitute, you will get shear force. So AX into HD of multiply with AX. So AX is equal to X, HD is equal to HD is WX by L by 2. So now half WX square by L by 2 here 2 WX square by 2L will get cancelled here WX square by L you will get. So this is total load on the beam. Sorry, the load on the AX length AX length beam. Clear? So now substitute in shear force equation. Shear force is equal to RA minus what is the load? Load on the beam length AX. So RA is equal to WL by 4 minus the load on the beam length is, now we calculated here, WX by L by 2. So WX square by L, WX square by L. This is shear force at section X. Now calculate shear force at point A. Point A. The point A, X is equal to 0. So the shear force at A is WL by 4 minus W into 0 by L. So W by 4. Similarly, shear force at X. Shear force at X. WL by 4 minus WH square by L. Next, shear force at C. WL by 4 minus WH square by L. So W into what is the X here? L by 2. So WL by 4 minus WL square by 8. WL square by 4 and 8L. So LL get cancelled here. WL by 4 minus WL by 8. So 1. So here take LCM. 8 is LCM, 2 WL minus WL. So finally we will get WL by 8. So at B point, the shear force is at B is L. So that the X is equal to L. At B, what is the shear force? X is equal to L. So the WL by 4 minus WL square by, so WH square by L. So WL by L square by L. So now it will get cancelled here. So we will get here WL by 4 minus WL minus 3 WL by 4. So here calculated shear forces. Now draw the shear force diagram. So shear force diagram, draw the shear force diagram. At A, the shear force is WL by 4. Positive value. At C, shear force is value. What is the at C value? At C is equal to WL by 8. So here the load on the beam AX we calculated. So that is XD is equal to X W into X by L by 2. L by 2 XD is equal to. Now substitute in this equation in this AX is equal to X and XD is equal to WX by L by 2. So 1 by 2 WX square by L by 2. So 2 WX square by L. So 2 get cancelled here, WH square by L. Finally the value. So like this calculate C at point C, you will get the value, and then here calculate, sorry. So WL square by 4 by L. WL square by 4L. So that's why WL square by 4L. Now WL by 4 minus WL by 4 you will get 0. At C point there is no shear force. So that's why here the value is 0. Again the shear force changes its sign positive to negative at B WL by 4. At B WL by 4 at B point at X is equal to L, at X is equal to L, WL by 4 minus W XL square by L. So here WL by X is equal to L, WL square by L. So we will get at B, RB, at point B, the shear force is WL by WL by 4, that is negative value. Clear? So now draw this diagram. This is a shear force diagram for this calculated shear force. Now need to calculate bending moment. So the bending moment at in similar fashion calculate the bending moment equation. So the bending moment is so the bending moment at section X. So that is mx. So as is equal to, as per diagram, RA multiplied with x minus the load on the beam length AX multiply with the acting is the distance is x by 3. So now substitute RL WL by 4 multiply with x minus load on the beam length AX is equal to WH square by L multiply with x by 3. This is bending moment equation. So now calculate at point A, x is equal to 0. What is the bending moment? Substitute x is equal to 0. The bending moment is 0. At point B, at x is equal to L. For this also, the bending moment is 0. So from A and B, the values are, the bending moment is 0. Now, need to calculate bending moment at point C. So the bending moment at point C, what is the value distance is L by 2. The bending moment at point C, x is equal to L by 2. So now substitute in this equation WL by 4, WL by 4 into x minus WH square by L, WH square by L multiply with x by 3. So the x is equal to L by 2 minus WL square by 4L dl by 6. LL get cancelled. So here WL square by 8 minus WL square by 24. So the LCM, take LCM. So WL square by 2 WL square by 24. So we will get take LCM here 24 3WL square minus WL square 2 WL square by 24. So you will get finally WL square by 12. This is bending moment at a point C. So this is a positive bending moment and maximum bending moment will occur at C. So now draw the bending moment diagram. So as shown in figure in this, the bending moment WL square by 12, the maximum. Positive bending moment, only positive is there. At B, A and B, the bending moment is 0. So like this, need to draw the bending moment diagram for a given beam diagram, load diagram. So here, first I need to calculate load on the beam length AX, and then calculate the bending moment at each and every point A, B, and C. Clear? So you will get the major bending moment at a point C. Clear? Next one, simply supported. Next case is simply supported beam carrying a uniformly varying load from 0 at one end to W per unit length at the other end. Now, previous case we have seen only at its center, but here the simply supported beam carrying uniformly varying load, this one also carrying UVL, but 0 at one end. But the W per unit length at the other end, so the load is maintaining. So here the figure I will show you, the beam AB of length L simply supported at the ends A and B and carrying a uniformly varying load from 0 at end A to W per unit length at B. First calculate the reaction forces at RA and RB. So that the given load diagram is like this. RA and RB, and at section X, the distance X, the load is acting. At section, the load is acting, you need to calculate. The 0, the uniformly varying load, this is UVL, W X by L, so W at other end acting W per unit length. 0 to W acting. So in between, need to take section and then calculate the shear force at A and at X section and B section. So load diagram drawn. So and then the shear force and the bending moment diagrams for a simply supported beam carrying uniformly varying load for length at the other end shown. So need to calculate here first RA and RB. So RA and RB is the total load on the diagram, total load on the beam. So the total load on the beam, how do you calculate the total load? The total load on the beam is the total area of the diagram. The total load on the beam, is equal to area of the triangle. Area of the triangle, what is the triangle here? A, B, O. Area of the triangle A, B, O. So how do you calculate? Half multiplied with AB multiplied with BO. BO. So now calculate this area of AB is given length L and BO is W. So WL by 2. So the total load on the beam is WL by 2. So but here this load is not equal to half of the reaction force loads are not half of the total load. Why? Because this is not symmetry. In previous case given like this, so the load acting at its center only, that the two ends 0 0, so that have taken symmetry, half of the total load. But here varying 0 to W, so need to calculate, need to take moments about A or about B, taking moments of the forces. So here taking moments of the forces about its about its point A or B. So now take moments about A, moments about A, RB multiplied with L is equal to RB multiplied with L is equal to, so W, so what is the length here? The UDL, the center of gravity, 2 by 3rd WL. Need to take here 2 by 3rd. So the RB into L to W multiply with 2 by 3rd W. So here so RB is equal to, so RB is equal to, RB into L is equal to 2W by 3L. So here now calculate RB. RA plus RB is equal to total load on the beam. So WL by 2. So 2 by 3rd. So WL, W by 3L. And now calculate RA plus RB is equal to WL by 2. So now WL by RA is equal to, RA is equal to, so WL by 2 minus 2WL by 3L. So in this diagram, So WL by so WL by 2 minus 3L. So here 3WL minus 4WL. So minus WL by 6. So here the minus WL by plus WL by 3. So here the force is the total load they have taken WL by 2 and WL by 2, the total load on the beam. So WL by 2 have to take WL by 2 and 2 by 3rd into L. Sorry, here taken wrongly here WL. So LL get cancelled here. So 2 get cancelled here. WL by 3 RB. WL by 2 minus WL by 3. So you will get WL by 6. RB value WL by 3 and RA is WL by 6. So now calculate the shear force. So take section at X. So now take shear force at section X. So that is Fx. RA minus the load on the length of the beam. Load on the length of the beam. Length of the beam AX. So RA WL by 3 minus load on the length of the beam AX. So the load on the beam length AX already calculated. Load on the beam not calculated here. So the AX, so take AXC. In this AX multiply with CX. So AX is equal to X and CX is WX by L. So now load on the length beam AX is equal to area of the AXC. So of multiply with AX is equal to X. AX is equal to X. Multiply with XO XC WX by L. WX by L. So now calculate WL by 3 minus WX square by 2L. So this is shear force equation. Now calculate shear forces at different points. Now at a point A, x is equal to 0. X is equal to 0, substitute WL by 3, WL by 3 minus W by 2L. So W into 0 by 2L, so 0. So WL by 3. At B, x is equal to L. So that WL by 3 minus WL square by 2L. WL square by 2L. So LL get cancelled here. WL by 2. WL by 3 minus WL by 2. So you will get WL by minus WL by 6 at B. At section X, the value is X is equal to X value. So already we have calculated at X is equal to that section X is equal to shear force. That is this is Fx, RA minus load on the beam. Similarly, calculate bending moment. So the bending moment is the bending moment equation. The bending moment at section X. The bending moment at section X, that is by mx, is equal to RA into X minus the load on the beam length AX multiplied with 2 by 3. So now RA WL by 3 into X minus the load on the beam length AX. So already have calculated here AX is equal to the load on the length AX is equal to WX square by 2L. So now calculate bending moment at point A and point B and bending moment at X point. Already have calculated. So after calculation, so there is a bending moment variation between A and B according to the cubic law. So the bending moment occurs at a point where shear force becomes 0 after changing its sign. So that point is at a distance of L by 3 from A. So that is substituting X is equal to L by 3 in equation and get maximum bending moment you will get. For maximum bending moment apply this equation. So you can see in this the shear force and the bending moment diagrams are drawn like this. The A is equal to WL by 6 RA have calculated. RB is equal to WL by 3 and C calculated at C. There is no shear force here. So the positive to negative, the shear force changes its sign, and then the bending moment follows cubic law. So positive bending moment will be occurred. That is maximum bending moment is WL squared by 9 root 3. So need to draw the diagrams of shear force and bending moment diagrams for given condition and beam, the type of beam, and to draw according to the calculated shear force and bending moment values. So this is the variation between uh, the simply supported beam carrying uniform UDL or UVL, uniformly varying load, at its center, and then 0 to varying 0 to W. So we have seen these three cases, differences also on here we have discussed. So these are the references I have taken for this PPT. Ramamrutam. The title of the book is Strength of Materials. The publishers are Dhanpati Rai and Publishing Company. And the R.K. Ross book, Strength of Materials. R.K. Bansal, Textbook of Strength of Materials, Lakshmi Publications. And R.S. Gupta, the Strength of Material textbook have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.